address of entry point. That's just the RVA of where you're going to start executing code. Image base is where it prefers to be located in memory, virtual memory. Section alignment and file alignment are just, whether the memory addresses are aligned on some alignment or the file addresses. Size of image is the total amount of virtual memory necessary to map this executable into memory. DLL characteristics, that had the things like ALSR, dep, and signatures. But then there's this data directory one down here at the very bottom. And so data directory is sort of the key to all of the other specialized components of the P file. So this right here on this picture is the data directory. And so there's image number of directory entries. That's hard-coded to 16 on Windows. And while the file header.size of optional header could technically change that, in practice this is always fixed to 16. John, could you grab that door? I mean, they should be back in a second, but until then. Oh, there they are. All right, so in practice, this data directory is always hard-coded to 16 entries, and each of them is, a structure called. Let's see. Each of them is a image underscore data underscore directory data structure, but that's really just a very simple thing where it's a RVA and a size. So each of those elements of that array is just this 2D word data structure. There's a virtual address, which this is actually an RVA again, and then there's a size. And the size is pointing to, so the size is used for, sometimes this RVA points at like an array of structures, sometimes it points at one structure, but it's really, the size is more for, if this virtual address points at an array of structures, the size will tell you how many of them you should expect based on the size of that data structure they're pointing to. Yep. So, this is not going to work for me here. So here are all the different types. Well, here's the names for the indices basically into the data directory. You've got index 0 is export, 1 is import, etc. So these are basically all of the major types of data that you can find in the P file outside of that initial file header, section headers, and optional headers. So we can have export data, we can have import data, we can have resources, exceptions, security. I think the security one is the digital signature actually. Relocations, debug information, etc. So we're actually going to go through a bunch of these and dig down into each of them in order to figure out what sort of data they have. And yeah, this is the point at which there would be a pop quiz and the audio and visual and everything is not working, and that's why I need my Mac working. All right, so this is the pop quiz. So this is our DOS header. And now the question is, which of these fields do we actually care about and why? So let's see. We'll call on Eric. Give me one field of the DOS header that we care about and why we care about it.
You care about the magic number so you can tell if it is a P file?
Right. Yep. So we care about the eMagic, the very first one, in order to tell whether or not this is a DOS header. So this will have the, do you remember what the value is that it has there?
MZ.
Yep. So it has the ASCII characters M and Z as these 2 bytes, right? So it's a word, it's 2 bytes. And so it's ASCII character M, ASCII character Z. And that, tells us that if we're just looking at some location, that's our little sanity check that, okay, this is probably a DOS header. All right. What else do we care about? Right. It's almost as if it's supposed to specify a file address of the new exe header. Yes, it's the offset to the next data structure, the NT data structure, which has that file header and optional header. Oh, we'll see that's there still, but no audio. Okay. All right, so now we're going to come back to the data directory once we dig into each specific element of it. But for now, we're just going to talk about the section headers a little bit first, because sections are sort of a common notion amongst binary file formats. So the purpose of a section is that it's basically grouping a bunch of similar data or code into the same regions of memory. And so Typically, it's in order to enable the same permissions on that memory, where permissions are your typical read, write, execute type permission. So, and specifically, sections are going to have their own names, where the name will typically give you a notion of what kind of section it is and what it's being used for by the compiler. So, a common thing is that the .text section, that's going to have code in it. So you should always think if you see a .text section in a binary, that's going to have a bunch of code in it. That's going to be executable memory. .data section is read-write data. Potentially, this could be the kind of thing like a global or something like that. So if you specify that there's a global in your C file, then where that global is actually stored, it's not going to be on the stack like all your local memory, like all your local variables. Globals will go into this .data section, which will have some location that it's mapped into memory. Our data is sort of like global data that is read-only. So something, whenever you like, hard code a string into like a parameter, if you're like passing a string and you just put a quoted string and you pass it in. So we said that we don't push strings out of the stack when we're pushing them into, when we're, calling a function, we push the address of the string. And so the address of a string is almost always going to be something like in the our data section, for instance. So later on, if I remember, if we get Visual Studio working on here, I can show how, we can make a simple hello world, we give it a global, we give it a string, and when we look at the addresses, we'll see that these will the addresses for a string or the address for a global. If we go back to the PE headers, we'll look at the section headers, and the section headers will say this chunk of memory is .data, this chunk of memory is .our data, and then we'll be able to see those addresses were within that memory range for .data or our data. BSS, which I'm going to say is block storage start. This is basically memory where it's for uninitialized global variables and things like that. The type of data that you would get in the .data section, but anything where you don't initialize it to a value to start with. And so the BSS, the point is sort of to save space on disk. So if you have a variable and it doesn't have an initial value, and it's not like a stack variable, right? We know the stack variables come and go as we create stack frames. But if you have like a global variable, but it doesn't have some initial value, you don't need to store that on disk. You can basically just allocate some chunk of memory, and you can assume that the OS loader is going to make this BSS space, and then at load time, the OS loader allocates space for this section, and then the code, which was actually compiled, can reference addresses into that section where it'll just say, the first address is, global 1, the first address plus 4 is global 2, the first address plus 8 is global 3, etc. And so the code will just assume that will be there at runtime, but because that didn't have like some hard-coded value which it needed to be set to start with, you don't need to actually store that on disk. And so it's a case where you just allocate memory, but you don't need to store on disk. Whereas something like those string values, right, you couldn't have hello world unless somewhere on the binary there was the hello world string stored where we could find its address and pass it to printf. So something like the strings and the our data or the data section, those have to be stored in the binary, but BSS is for anything where it wasn't initialized, therefore you don't have to store it on the disk. Technically, there's an iData section, which is where import data is. As we'll see later, a lot of these sections get all merged together, so anything that has similar enough permissions, the linker will sometimes just like blob all of that data together. But conceptually, iData is, if you see a section called iData, what it's trying to tell you is this is where my information about what functions I import from external libraries is stored. And actually, we only see that ever on debug builds on here. If we do a release, or if we do, a release build in Visual Studio, it'll merge it in. But if we do just a debug build, then it won't merge it in. So we'll see that hopefully. Then different things called page. You'll see these like it'll just called page or page lock or page KD and things like that. Sections that have names that start with page, these are typically used in like kernel modules, and they're basically saying this data right here, it's like a .text section, except I'm telling the OS loader, go ahead and feel free to page this out to disk whenever you want. So whereas the .text section in a kernel module, it's marked as non-paged, and what it's saying is this code better be in memory all the time because people could come be like, people could be trying to call this code at any given time, and if it's not in memory, potentially that'll blue screen the system because it could be running at a permission such that you can't pull it in from disk in time. So page is used to say, this is code, but it can get swapped out to disk if you want, if the OS is running low on memory. And .text is typically going to be marked as non-pageable and therefore always in memory. .reloc, that has to do with the relocation information, which we will keep referencing a bunch until we eventually get there towards the end to talk about it. And .resource, I just pronounced it like resource. .resource is where resources go, and resources are things like icons and miscellaneous data. You can embed actually binaries within the binary as a sub-resource and stuff like that. So talk about resources later as well. So what we're talking about right now are these section headers right here. And so I've listed a bunch of names, so yeah, there better be a name file in there. Yes, question?
Quick question about this. How about, it seems like so .text sections code should never be paged out to memory.
Yep.
But page seems to be code not in spec. Where does code generally go? I mean, yes, most programs have a lot of code that can be paged out. What section does that go into?
I would say, well, so primarily, as far as I'm aware, the page stuff only gets used when generating kernel modules on Windows.
Right.
So what would happen is, it would be the kernel module developer's responsibility to say, this code is critical and must never be paged out. So they would have to mark it specifically as non-paged, and then it would go in .text. Otherwise, it would go into page by default, unless the kernel developer said, you know, it must not be paged.
I'm not exactly back on the turn. I'm talking about Word, for example.
Right. In .word, I believe in that case, yeah, so this, you might be right that I was too absolute here by saying .text is code which should never be paged out. I'm probably thinking kernel, but in that's not necessarily the case for all things, right? So let me go try to prove this assertion or disprove it. I'm going to open up pview and look at something like Notepad. Right. Yep. Yeah. So I've probably scratch out the .text is code which should not be paged out kind of thing. So it's code and it may or may not be paged out. I'm thinking to kernel module. So under this characteristics, actually, we talked about it a little bit before. There's, oh, sorry, we haven't talked about it yet. There's a characteristic that says don't page me out. So I'll show that. Right. .text is just code and yeah.
Where do they store the debug symbols? I guess for Windows, they must store them. I think they store them in a separate file.
Right, it is in a separate file. There's a little, we'll talk about the debug section. Back in this data directory stuff, right there, there's an entry in the data directory that is a little pointer to something that points you to some external file for debug symbols, potentially. Or they could be embedded, but nowadays they're not. All right. So yeah, we got to talk about what's actually inside of the section header. So we know there's going to be a name because I just was talking all about .text and stuff like that. That's all in this name field. But yeah, so the name is an 8-byte array. It is, the name is not guaranteed to be null terminated, for instance. I'm jumping ahead, but. Okay. First, let's do a refresher on unions. All right. One of the members of the section header is a union, right? And so it's union of physical address or virtual size, and the union is named MISC. And so as a reminder for unions, how it works is that there's only one D word there. It's not like a structure in that there's 2 D words, right, which you can access each of them. With a union, there's only one D word, but you can access it by 2 different names. And you're basically going to access it with one name in one context and one name in a different context. But this one is easy for us because we'll only ever access this as the virtual size field. so the physical address is never used in, as far as we're concerned. I'm actually not even sure if it's ever used anymore, but there again, if anyone finds where physical address is actually used, let me know. All right, yeah, so union, basically how we're going to access this virtual size field is it's actually misc.virtual size, as it says right here. So if you have some section header, and you're like, parsing the structures, well, if you're just accessing the structures, you'd have a section header, and then you'd have a field misc, and then because this is a named union, it's misc.virtual size in order to access the virtual size field. All right, so onto the name. The name is just an 8-byte array. This is where you store the things like .text, .data, etc. It's in this name array, but the array is not guaranteed to be null terminated. So that means if you have something like, I don't know, page, the page ones are frequently too big, but, well, I can't think of one at the moment. So you can have names for sections where if the name is 8 characters long, then there's not going to be any null character after it. So just, you have to keep in mind, don't ever try to use like string copy functions or anything like that if you're trying to copy the name out of a section header. Otherwise, if it's a long name, you're going to buffer overflow. All right, and then virtual address. This is basically saying this is the RVA of where this section is going to start in memory. So we said, the entire binary is going to get all of the data from, well, not all of it. Most of the data from disk is going to get mapped into memory. And these section headers are basically saying, for this subcomponent of data on disk, I want you to map it into memory here at a certain size. So the virtual address is saying, for this .text section, right? So .text is going to be a bunch of code. It's going to be a bunch of assembly that's just stored as bytes on file. And it's going, this section header then, when the OS loader is loading the binary, it's going to read the section headers. It's going to see, okay, I see you have a .text section. Your name is .text. It doesn't really care about that. That's just for the humans. You got .text, and what it's saying is this data is going to be mapped into virtual address, virtual address here, where this is an RVA. It's a relative offset from the beginning of the file. And specifically, that's where it wants to start loading it in memory. Virtual address is where it should start going in memory. Pointer to raw data is where it should start reading from file. So pointer to raw data is a file offset into the file on disk. So if I have Notepad on disk and I have the .text section, it's going to say, okay, OS loader, read pointer to raw data into my notepad.exe and start grabbing data at that location and put it into virtual memory at virtual address. And then, of course, obviously, we have to have things like size, right? So we need to have a virtual size and a size of raw data. So the size of raw data is the actual bytes that you read out of disk. So OS loader goes to disk, starts at pointer to raw data, reads size of raw data, worth of data, off of disk, puts it into memory, starting at virtual address, and then the total size in virtual memory is virtual size. So the problem here is we can have two cases, one of which is virtual size is greater than size of raw data, and the other is size of raw data is greater than virtual size. So this gets a little confusing here, but yes?
So the linker figures out the RVA of where it needs to go, and then it gets resolved at load time with the virtual address of the operating system.
Right, so the linker, yeah, can basically just say, it can really pick whatever RVA it wants, and the linker just puts down some values into this header, and that's how it's going to, how the loader at load time is going to place stuff into memory. So it could, arbitrarily slide stuff, greater than, it could keep putting them farther offsets, but in general, right, it's going to try to minimize memory usage, right? So it's going to try to choose, well, let me show a picture quick. Over to the board. Well, hold on, let me see. I'm jumping ahead. I have the next picture. So let me answer that question then with this picture, basically. That picture is messed up. All right. So notionally, well, what I wanted to consider here was the notion that virtual size is greater than size of raw data. But the point here is well, no, sorry. I'm going to go back to just as a high-level overview board. It's something like this, right? So if we have the total module address space, and this is notepad.exe, and this is image base, right? Whatever that is, call it X. I don't know, maybe. All right, so let's say notepad.exe got loaded into memory at 400000, whatever. There's going to be, so when it's loaded into memory, there's going to be some headers right here. And then there's the file on disk. So this is, let's say, in memory. This is on disk. So the file on disk may be smaller than the file in memory. That's where that size of image is the total size here. This was optional header dot. And that was optional header dot image base is saying like it starts here, optional header of size of image says allocate that much total memory. So inside here we had the first headers right there, and then we said after the NT header and the DOS header, we had like an array of section header type information, right? So we call this section.text, section.data, right? So we've got a bunch of these things, and what it's saying is, these are still the headers. This is then like the actual, real.text data. And this is the real.data data. So this header says basically, dear OS loader, take this real text data, read that chunk of it right there, and map it into memory right here, wherever. And so the thing is that virtual address field right here. Right, so we've got 4 fields. We've got a starting physical address. We've got a starting virtual address. We've got a starting physical size. We've got, or physical meaning like disk size. And then we've got a, not starting physical size, we've got a total disk size and a total memory size. The virtual address field is basically saying, that's the field which is saying, that this section for the .text says, take this data off of disk and map it in at RVA, hex 1000 or something. So this could be an offset hex 1000, right? And the absolute virtual address, like I'm going to call that absolute virtual address, equals x401000, right? So the absolute address right there is the base plus the displacement. And then it's just saying, because my, virtual address is hex 1000, map this text stuff into here. And so each of these headers, in turn, specifies some mapping, into things right here. And there may be a gap here. There may be a gap, there may not be. They can try to but ideally, what the linker should be trying to do is, try to reduce this overall amount of memory that's being used, right? Less virtual memory means less physical memory means more physical memory for other programs, etc. So that's all really this section header is trying to do, is say, let's map some chunk of this file into memory starting there. Does that answer the question there?
It does. But the image, kind of. The image, I'm just kind of getting I got a question about how the loader, what kind of conventions the loader uses to ease the operating system.
I think you mean linker, yeah. The loader just reads whatever. Right, so what conventions does the linker use in order to, how does it choose where it's going to put these? In some cases, it will potentially, always set these as starting addresses being some virtual, like offsets section aligned, right? So we have that section aligned hex 1000 potentially. So this could be 1000, that could be 2000, this could be 5000, et cetera, right? So it may try to align those on section things. Other times it'll just try to compress stuff as close together as possible. So if it does it on aligned boundaries, it's doing that just so that, well, potentially so that any internal code will match, you know, alignment guarantees, because for optimization purposes, sometimes they want, so if the compiler, for instance, output code which assumes that like it's behaving well, it's well behaved with respect to like Intel alignment policies and stuff like that. So Intel will say, you know, calls to function, like functions must start on 16-byte aligned addresses or something like that. And so the notion is if there was some code which was wanting alignment things, if your actual entire section was like off by a bit, you've just broken all of that code's optimization, right? So optimized code would in turn try to potentially allow mappings which would allow for that code to still be optimized, because if it was off by one in its mapping, then it would no longer, none of it would ever be 16-byte aligned, basically. So all I can say is sometimes it'll try to align it for hand-wavy sort of alignment and optimization type things, and other times it'll just try to compress down and use as little space as possible. All right. So yeah, we saw almost all of these now except for the characteristics, right? So we saw the name, that's just your .text, etc. Virtual size, that's saying, well, you got the picture. So, all right, so let's go back to this and consider this quick. So the interplay between virtual size and size of raw data. In some cases, virtual size, so the amount of memory that it takes up, will be greater than the actual data that you have on disk. And so the most common reason for this is that .bss section that I was talking about before, right? So the BSS section is someplace where you don't need any data on disk because the data has no initialized initial value. So if you don't need the data on disk, all you need is to allocate some amount of virtual size. The size of raw data could be 0. And so this is an example of, you know, what that might look like if for instance, the .bss section was like tacked on to the end of like the .data section. So here we have, you know, on disk, we can have a section header that says, okay, well, my virtual size of what I want it to be in memory, my virtual size should be hex 300. My size of my actual data on disk is hex 200, right? So I know it's going to be bigger in memory than it is on disk. So this is my size on disk, hex 200. This is my size in memory, hex 300. And so I've got a pointer to raw data saying, okay, read 500, hex 500 bytes into the disk. That's where you're going to find the data. Take hex 200 of it, map it into memory, but then also you should also have another extra hex 100 worth of space because I want hex 300 worth of virtual space. And so, so what that would look like basically is, let's see, first of all, yeah, this is again, chalk this up to not having the right slides showing, but, you know, this over here, we're saying that this, you know, this is not to scale, obviously. You know, here this is hex 500 into the file. Here this is hex 1000 into virtual memory. So we're saying because the virtual address field of the section header said map it into virtual memory at offset hex 1000, then it goes down hex 1000, starts mapping the data from disk into that location, but it has a total of hex 300 worth of data, or worth of virtual memory allocated, and so all the rest of that's going to be 0 initialized data due to things like old school Orange Book criteria about like not leaking data, right? So this data is 0 initialized because if you just allocated some memory that this program could access and you didn't 0 initialize it, then potentially you'd be leaking data from other processes and stuff like that. So for Orange Book purposes, we don't want to leak data between processes. So this is a case where virtual size is greater than the size on disk. So we got more memory than we have on disk. There is a case, though, where size of raw data could be greater than virtual size, right? So when would you have more data on disk than you actually want put into memory? This has to do with that optional header.file alignment thing. So I said if the file alignment is hex 200 or something like that, you must write data to this executable in chunks of 200. If you've only got, you know, a single global variable 4 bytes worth of data. Doesn't matter. The file alignment says you got to stick it in there in hex 200 chunk. So you may put the virtual size to be 4 to say, look, I've only got 4 bytes of memory that I'm actually going to access. But the file size could have been 200 because that's just how big the aligned chunk was. So this is an example of that, basically. Here, pointer to raw data, again, is hex 500 into the file. And the section data right here is, well, the size of the raw data, the entire part of it right here is hex 200. So we know we've got hex 200 worth of data, but in reality, only some subset of that is ever actually accessed by the running program. So the OS loader, it may copy hex 200 worth of stuff in there, but it's actually only the virtual size chunk of hex 100 which is ever accessed by any program. So that's trying to also tell you that potentially, well, no, I'm not going to say that. So that's just trying to say that the virtual size is the only data which is ever actually accessed by this thing. So that would matter to you, for instance, if you're reverse engineering something. If you see data changing outside of the virtual size, you can see someone's like playing around with their headers, right? So a legitimate compiled program, the linker will just create a section header that says, look, virtual size, that's how much I'm going to be accessing, right? It may be bigger than's on disk. That's fine if it's .bss. But, if it's smaller than on disk, then any access outside of that is potentially the code understanding what's going to be going on with the OS loader and just manipulating it and playing with it. All right, and then finally, there's the characteristics on the section header. This is where you get your typical read, write, execute type characteristics. So I said the whole point of like glomming together a bunch of code and a bunch of data is so that they can have the same characteristics in memory. And so this is where the characteristics on the file header say, look, this chunk of memory which I'm mapping here, starting at virtual address, going for virtual size, this is code. I can say this is code. I can say this is executable, and I can say this is readable, but maybe I don't want to set it to writable, right? Something like that. Because this code, let's say it's not polymorphic code, it doesn't need to write to itself either. Normal code is not going to need to write to itself. Then my data, I may want to write my data into memory. I can say, okay, well, it should be readable, it should be writable, but should not be executable, it should not be code. And, maybe I want it to be shared, and maybe I don't. But this shared then has to do with that thing we were showing before with those two process address spaces that can potentially share the same data between them. The shared would be used to signal to the OS loader that it can potentially share these amongst different processes. This discardable one is actually interesting. That's something where this section can get loaded into memory initially, like right when the OS loader is running. The OS loader is going to use it for something, but then it's going to throw it away and reclaim its memory immediately. So I had some problems on my project a long time ago dealing with memory which was marked as discardable because I assumed it was in memory because I didn't know about this discardable characteristic. But just because it says that, it's in the section headers, if it says it's discardable, you can't guarantee that it's going to be in memory anymore if you come in at some later point and try to read that memory. Yes? What? What would you use that for? The most common thing is the relocation information. So again, I just keep making reference to it, but resources and relocations, I think, are actually both discardable. So one thing is the relocation information is only necessary by the OS loader if it's going to move this binary in memory. So if you can't get your preferred address, the OS loader needs to move it. That relocation information is just all the little helper stuff for the OS loader to say, here's all the places that need to be fixed if I move this in memory. So after it does the fixing and it puts it into memory at its new location, it doesn't need the relocations anymore. It can just reclaim that memory. The other thing is the resources like, icons and stuff like that, basically. So they don't necessarily need that after load time. Depends on what the resource is, though. And then here's a bunch of fields that aren't used anymore. So don't care about those anymore. All right. Miscellaneous thing is that you can rename sections. So whereas I said that, you know, if you see a .text section, you can think to yourself, okay, that's probably code in there, right? But, you know, we can rename them to whatever we want, and the OS loader doesn't care at all. It's the names of sections are really just for the humans to understand the conventions behind them. Conventions like .text is code, .data is read-write data, you know, .r data is read-only data, stuff like that. So that's where you do it in Visual Studio.
How does it know what code is?
So it only knows where the address of entry point is, right? So in the optional header, all the OS loader needs, the OS loader doesn't really care about code and stuff like that. It cares about, you know, permissions. It may say this characteristic says I should mark this as read, write, execute, or I should just mark it as read, write, something like that. But it really, it's, as far as code goes, code can be anywhere that memory is marked as executable, and the first code must be wherever that address of entry point is, because that's where it's going to jump. And if it's not marked as executable, then you're going to have a problem. And then, yeah, this has to do with merging sections. So when sections have similar properties, like if they're both just read-only data, stuff like that, then you can just merge them together, and it'll put them together. It'll take all the data, put the data contiguous, so that they get mapped into memory, and then they're going to get the most permissive permissions of the two of them merged, basically. So if one section is read-write and one section is read-write execute, if you merge them together, you're going to get a new big read-write execute section. So here we can see actually I did this sort of merge here to my .data into the .r data, and it's saying, well, you know, these are completely different, well, these are different attributes, but the output result was something that had the permissions of .data, so it was read and write as opposed to just read. And this would be another pop quiz. Pop quiz, hot shot. I'll say it instead of what he says. All right, file header. So we talked about the file header a little while ago. Let's see who remembers anything about it. John, what's a field that we care about in the file header and why?
Number of sections.
Yes, thank you for saying it to that degree. Yeah, so it tells you the number of sections in the array of section headers that immediately follows the optional header or the NT header, since the optional header is part of the NT header. All right, so number of sections is the only way that you're going to know how many well, the only way the OS loader, or you if you're parsing it, is going to know how many section headers are following the data. Another field, read.
Sure, the time date.
All right, why?
For one thing, it tells when the particular binary is compiled, so you can differentiate between different versions of potentially two pieces of software that might be the same version, or you can use it for malware attribution patterns.
Yeah, so you can use it for sort of forensic analysis of things, or you can just use it to try to differentiate, you know, two different versions of the same code, essentially. Rob? Nope, that one's not used.
That one, yeah, I just said that. Right?
Nope.
Someone else already took the two I immediately thought of.
No. Amy? Characteristics, yes. Why do we care about it, though? What's a characteristic that we have in the file?
The only one I remember is whether or not it's an
Yes,
executable.
so that was one. Right, there was like executable, there was like DLL, there was like 64-bit compatible, things like that. So we said this is the characteristics field that is of lesser importance as far as I'm concerned relative to the DLL characteristics, which was the ALSR and DEP and stuff like that, or that section header characteristics, which is your read, write, execute permissions. But yes, that's correct. And that's it for this one, in terms of what we said we cared about at least.
The size of the optional header is always the same.
Yes, so the size of the optional header should technically be always the same. in a well-formed PE file. You can play games with it, as we'll see hopefully on the tomorrow towards the end, or hopefully towards the beginning. All right, let's see, static linking versus dynamic linking. All right, so now we're going to, let's see, I'm just going to go over this before because this is going to be a big old section. So before I get into this, we're just going to conceptually talk a little bit about static versus dynamic linking, and then we'll take a quick break. I already sort of made reference to this, but when I was talking about executables before, with static linking, what happens is you're telling the linker, I want you to take all of the code everywhere that my executable depends on and put it all into this single binary. In dynamic linking, you're telling the linker, okay, well, if you can't find something, but you know it's in some dynamic library, go ahead and just put a reference to say import libc, import mylib1.dll, things like that. So static linking is throw all of the code into one place, and dynamic linking is basically, we have these libraries, DLL files, .so files, they're off to the side. They can be reused by multiple programs, and so if I need something in that library, I'll just go ahead and put a reference into my, well, the linker will just go ahead and put a reference into my binary saying, I need something from mylib1.dll. So, let's see. Yeah, and so when it comes time to actually call those functions, essentially you're going to need some pointer to the function. And so dynamic linking, there's a variety of ways that we're going to go into about how that's actually achieved in order to, at runtime, figure out where the actual address in memory is of the function that you want to call. And so, yeah, like it says there, statically linked executables are like huge compared to dynamically linked executables because, you know, if you say that you require just printf or something like that, the thing is printf may require a bunch of other libraries and, well, a bunch of other code and things like that. And so every prerequisite for every piece of code that you use is all, you know, it recurses down and finds all of that code and it sticks all of that code into your executable. So, I mean, I think I have some examples later on in the ELF section about, you know, a dynamically linked hello world is not particularly small. It's maybe on the order of like 5 to 8K or something like that. But like a statically linked one is on the order of like a few 100K, maybe 500K, something like that. So statically linked executables are huge, but the benefit is it's all standalone, right? So you can take a statically linked executable from one Linux thing to another Linux thing, which has a completely different versions of libraries, and the statically linked executable will still work because it's self-sufficient. Simultaneously, then again, that's a bad thing. I think did I say it here? No. So that can then be a bad thing because if you linked in vulnerable versions of library code, for instance, right? So if a DLL that you were linking against had a vulnerability and you like glommed all of that into your thing, one of the points of DLLs is, okay, we can fix this vulnerability in the DLL, and now all of those executables that use that library are no longer vulnerable. But if you have statically linked code, then each executable that blobbed that code in there needs to be recompiled before it's going to get the fixed version. So they could be running around with vulnerable versions well after something is actually patched. So different trade-offs there between static and dynamic linking. So in terms of calling imported functions, we're going to just go to this level before we take a break. I mean, you as a programmer, this is completely transparent, right? You call printf and it just works somehow, right? And we saw to some degree, mostly in the intro x86 class, we saw calling functions where it's one of our functions. So if I'm main, I call, you know, subroutine sub. That sort of call is just a relative displacement kind of call. It says, you know, whatever my next instruction is, plus or minus something, that's where I want you to go next. In like maybe one or two instances, I guess we had printfs and we had like A2I and stuff like that where we're calling some imported function. When you're calling an imported function, it looks roughly like this. And so the first thing I'd call out again is we have that notion that like string data goes in the .r data section now. We said there's some chunk of memory where, you know, you have a section header that says all of this data is read-only and it should get mapped into memory at this location. If I went back out to this executable, my hello world, and I tried to figure out, you know, first of all, my base address is probably 40000 something. So this is my base address, and then there's some relative offset into my base address. If I looked where that relative offset fell, I would expect that would point into an RData section because this is just the address of a string. We've got this format string. We push the address onto the stack when we call because it's a character pointer, right? So I don't even know why I have that line. Oh yeah, I think I just copied this out from Visual Studio as it was. But so we push a parameter. We push some string, and I'm claiming now that this string is in the .rdata section somewhere. But then this call, it's saying call dword pointer ds, and then we've got square brackets. And so this is actually a memory address somewhere. And the square brackets are saying go out to that memory address, grab the value at that address, and then treat that like the place where we want to call to, right? So we're going to set our EIP to that, push the address to the next function or next instruction, etc. So we'd maybe seen this a little bit, but we just glossed over it. So now what I'm going to dig into is the fact that this address right here is basically part of a table of addresses. And so there's going to be a table of addresses, and each one of those entries in that table is the actual address of some function you want to call. This is called the import address table. And so in this case, I would expect that the value in memory at this address is the literal address of printf. So printf is going to be, whatever library printf is in, libc library, it's going to be mapped somewhere in this process's virtual memory space. And then some offset into that libc library is going to be printf. And so the OS loader at load time is responsible for taking this table of function pointers and filling it in with, it has to go out and says, okay, oh, you want printf? Okay, well, I'll go libc's there, offset to printf is there, and I'm going to take that address and stick it into your import address table. And this happens to be the specific entry in your import address table. So 5-minute break, and then we'll come back and really dig into import address tables. And quite frankly, that'll probably take the rest of the day. Well, there's like 3 different forms of imports.